For right now, though, let me give a definition for us. Let me blow this thing up first. Okay. Just a definition of similarity here. And there are a few different definitions of what it means for two triangles to be similar. I'm going to use this one. Two triangles are said to be similar if their corresponding angles are the same. I'll say are equal. How about that? Okay, so that's what it means for two triangles to be similar, right? And so like a 30, 60, 90 degree triangle is similar to another 30, 60, 90 degree triangle, right? They all have the same angles basically. And so why do we care about similarity? It's because like a lot of things that we can say about a triangle, right? All that matters is the angles themselves, right? The proportions of the sides are actually, and let me write this as a fact here. Fact. If two triangles are similar, then their corresponding side lengths are proportional. All right. All right. So we're going to be talking about trigonometric functions in just a second, right? And so the trigonometric functions, right? Those are basically just ratios of the different side lengths. And so because with similar triangles, it doesn't matter how much you blow up the triangle or how much you shrink it back down, they still maintain the same angles, right? Because of that, right? Sine of an angle is going to be the same thing as sine of another angle and a sine of the same angle in a different triangle, basically. And so that's why we care about similarity. So, I'm not going to go through the proof of that. It's kind of involved. I do have it here, but I'm going to skip past that and get on to the 6 trigonometric functions. Okay, so this is basically what we're going to be talking about for the rest of the semester. So, the 6 trigonometric functions. Looked on Wikipedia one day, and apparently, um, there were more trigonometric functions. Maybe some of them identical to the trigonometric functions we use today. Maybe some of them were just kind of pointless, right? But these are the 6 trigonometric functions that we talk about nowadays, anyway. Okay. So the setup here, right? We know we're talking about right triangles, right? Yeah. So we're going to define these inside of a right triangle. So let's let theta be one of the non-right angles in a right triangle. Okay. And we know that there are 2 angles which are not right, right? So we're going to let this be just one of those angles, okay? So let's just draw a picture, all right? Drawing a picture is always fun, okay? There we go. So we have this nice right angle over here, and then maybe I'll draw a theta over here, okay? We'll add to this picture in just a second. So there we have it. Okay, the side opposite, that only has one eye, yeah, okay. The side opposite theta is called, obviously, the opposite side. Okay, so what is the side opposite theta? Well, it's this side right here, opposite. And I'm going to use OPP as an abbreviation for opposite. Okay. The side touching theta, right? And maybe I should say, yeah, I'll say that. The side touching theta that is not the hypotenuse, right? Because, of course, the hypotenuse touches it. It's called the adjacent side. And all adjacent means is that it's next to it, right? So I'll do ADJ as an abbreviation for that. Okay. There's your adjacent side right there. We already know the hypotenuse, so I'll just use HYP for hypotenuse. Okay. So there's the setup for us. Might as well call this a definition. Okay. Okay. So usually with functions, right, we'll give them like a one-letter name, like f, g, h, f of x, g of x, h of x, right? Usually with functions, we do that. However, that's not always the case, right? You may remember from college algebra the natural log function, it's ln of x, right? And just general logarithm functions, right? log, right? Yeah, so we don't always do one-letter names for functions, right? And so the trigonometric functions are, well, they're important enough that they actually have, whole word names. Okay. So that's what we're going to do. We're going to define our trigonometric functions here. And I just want you to know that they are indeed functions. They have all the same rules that functions should have, right? Um, it's just that they have longer names. That's it. So, definition. In a right triangle, okay? A trigonometric function of an acute angle theta within the right triangle Oh, sorry. I meant the right. In a right triangle, a trigonometric function is a function of an acute angle. Sorry about that. Is a function of an acute angle theta within the right triangle. It's a bit sloppy. You know what? I'll just rewrite it. Yeah. No, I don't want to learn more. Okay, there we go. I'm sure you all say that. Okay. Okay. All right. So in a right triangle, a trigonometric function is a function of an acute angle theta within the right triangle. So that's all it takes in order to be a trigonometric function. Okay, so there are 6 trigonometric functions we're going to discuss, and I'm going to define them now. Okay, so I'm going to give it in a little chart here, right? I'll have a name for the function, their whole name, right? And then I'll have an abbreviation, right? And then I'll have what it's equal to. Okay, so just have a nice little chart over here. Okay, so the names of the functions are sine, S-I-N-E, cosine, C-O-S-I-N-E, tangent, right? And then we have the reciprocal functions, cosecant, secant, and cotangent. Okay. So that's the full names of those functions, right? But we abbreviate it as sine of theta, 3 letters, right? Cosine of theta, tangent of theta, right? And then cosecant is CSC of theta. Secant is SEC of theta, and cotangent is COT of theta. Okay. All right. And then now we got to say what it's equal to. Well, sine of theta is the opposite side length over the hypotenuse. Cosine is the adjacent side length over the hypotenuse. And tangent is the opposite side length over the adjacent side. Okay. Fair enough. And for the most part, that's the only 3 trigonometric functions I care about. I called cosecant, secant, and cotangent the reciprocal functions, and that's just because cosecant literally is the reciprocal of sine. Yeah, it is just the hypotenuse divided by the opposite side. Okay. Secant is the reciprocal of cosine, so the hypotenuse over the adjacent side. And then cotangent is the reciprocal of tangent, so we get adjacent over opposite. Okay. Fair enough. Can everybody read that okay? Yeah. Okay. So we can refer back to my picture above, right? So of the right triangle label with the opposite side, the adjacent side, and the hypotenuse, right? So we're literally taking those side lengths and just dividing them. We're looking at the ratio of those sides, right? And so because of that, right, if we're looking at a similar triangle, because similar triangles have proportional side lengths, you're going to get the same value for sine of theta in the big triangle as you would in the little triangle, right? As long as it's the same angle. Okay, fair enough. Maybe I'll draw a little picture over here, right? Here's theta in a small right triangle. Here's theta in a big right triangle, right? If these are similar, then sine of theta in the small triangle is the same value as sine of theta in the big triangle. Okay, call that a little note over here. Yeah. And I'm not going to prove it, but yeah, I mean, it would just follow from the previous fact. Okay. Okay. So any questions on that so far? On the definitions? Have we all seen these definitions before, by the way? The sine and cosine and tangent and the reciprocal functions. Yeah. None of this is new. Yeah. Okay. Then let's do an example, right? All right. Suppose the two triangles are similar. I'll draw them in just a second. Find the missing information. All right, so I'm going to draw two similar triangles here. At least I hope that they'll look similar. All right, I'll have the base being over here, let's say. All right. Let's see. Okay, maybe it looks like that. And then the bigger triangle, I will have that go. And these are similar. So I'll tell you that, let's say, oh, this one is a 30-degree angle. This one is a 70-degree angle. All right, this side length is of length 2, right? This side length is of length 3, right? Here's that 30-degree angle right over here, right? This side length is of length 4. This side length is of length 3, right? And then I want to know what this side length is. I want to know what this angle is, this angle, this angle, this side length, right? That's the missing information. Yeah, fair enough. Yes. Oh, this is a length to the sides of the triangle. Yeah. Okay. Now this isn't a right triangle. Okay. Yeah, neither of these are right triangles. Okay, but still we should be able to get some information just off the fact that it's similar, right? Okay. So let's see here. Let's see what we can do. Let's start off with the angles. How about that? Yeah. So the angles should be pretty easy. Oops. No. There we go. So since these are similar triangles and the base is over here, right, then this must also be a 70-degree angle right here. All right. Oh, you know what? I'll write it in purple to note that this is added information here. All right. So that was weird. Why not just go to the top then? Okay, there we go. So this is a 70-degree angle here, right? This angle right over here, well, we know that one of these is a 30-degree angle and one of them is a 70-degree angle. So that means that they have to add up to 180 degrees. So this must be an 80-degree angle up here, right? Fair enough. And then this is also an 80-degree angle. Any questions on that so far? Okay. Now, side lengths, maybe they're a little bit more challenging, okay? So remember that they're all proportional to each other, though, right? So maybe I should give some names to the sides. Yeah, here, I'll write those in green here. We'll call this side length A, right? This side length B, and this side length C. Okay. Fair enough. So A, B, and C. Okay. Again, not a right triangle, so they're not legs and a hypotenuse, right? Yeah. All right. So then now, because these triangles are proportional to each other, that means that this side length must just be some number times A. So I'm going to call it P times A. Okay. This side length over here, right, has to be proportional exactly by the same constant. So this is P times B. And this side over here has to be P times C. Okay. Any questions on that? All right. So then now, right? Well, we have some information here. We know that A is equal to 3, and we know that P times A is equal to 4, right? Fair enough. Yeah, so I've got this from the one triangle, this from the other triangle. Yeah. Any questions on that? All right. So that means that, well, since A is equal to 3, right? Then that means that P times 3 has to be equal to 4, right? And all I did was just replace A with what it's equal to. Okay. So then that means that P has to be equal to 4/3 by just dividing by 3 on both sides. Okay. And I know this is a little bit of algebra here, so are there any questions on that? Any questions at all? Sudden headache here. All right, so if we're all good with that, well, now we know what P is. That's actually really important. Okay. So here I know that B is equal to 2, right? So then P times B, which is this side length over here, right? P times B will just be equal to, well, I know what P is, and I know what B is, right? So P times B will be equal to 8/3, right? So here, this side length over here is 8/3. Here, I can get rid of, let's see, I'll get rid of this question mark here. And then I'll put that this is in red over here. No, in purple. This is 8/3 now. Okay. All right. I have one more question mark over here on the first triangle, right? Yeah, C is equal to question mark right now. I know that P times C is equal to 3, though. Okay. So since P times C is equal to 3, right? And I know that P is 4/3, right? I don't know what C is yet, but I know that this whole thing is equal to 3, right? So then I can divide by 4/3, and I don't like dividing by fractions. So instead of saying dividing by 4/3, I'm going to say multiply by 3/4. Yeah, 4/3 times 3/4, they multiply together to be 1, right? They cancel off to be 1. Is everybody okay with that? Yes. Oh, how I got this equation at the bottom? Okay, so I found P up here on the first line, right over here, by noting that I already have that A is equal to 3, and I already have that P times A is equal to 4, right? Yeah, so since I have those two facts, right, I plugged in that my A was 3 and I solved what P was. But that's exactly the same P in all of the side lengths over here, because that's what it means to be proportional sides, right? Yeah, that it has that same constant of proportionality. Okay. Yeah. Okay, so then now I can solve for C by multiplying by 3/4 on both sides of the equation. So 3 times 3/4 would be 9/4. Okay, so there we have it. So I get rid of this question mark over here, and then now I'll have that this is 9/4. And that's all the information about the triangle. There are 3 sides, 3 angles. There we go. Okay, any questions on that? Any questions at all? All right, so good. Now that I have that, right, so now let's do something involving right triangles. Okay. So find the values of the 6 trig functions of theta. Right, in the right triangle. And I'll draw a right triangle for you. Let's see. maybe it looks like this, and like this, and like this. That last side I don't like. Let's see. There you go. Okay, so here's our right triangle. I'm gonna call theta this one. Usually when I draw just a random right triangle, I'll put my theta right over there. It doesn't have to be there. It could be the other acute angle if you want to, right? Okay. And then here's some information. This is 1, this is 5. Okay. Fair enough. So I give you one of the legs, the opposite side, right? And I give you the hypotenuse. And then from this, you should be able to find what sine of theta is, what cosine of theta is, what tangent of theta is, and so on and so forth, right? Yeah, this is enough information, basically. Okay. Okay. So now notice when I haven't even told you what theta is, right? Doesn't matter. Yeah, you can still find out what sine of theta is. Okay. You can still find out what cosine of theta is. Okay. So, I'm going to start off this way. I'm going to find the missing leg right here. Okay. So by the Pythagorean theorem, right? Maybe this missing side length, I'll call that x. Okay. Right. That says that the squares of the legs sum together, right? So x squared plus 1 squared has to be equal to the hypotenuse squared. Okay. Fair enough. Yeah, so that just all comes out of the Pythagorean theorem. Do I need to explain that anymore? Are we okay with that? Yeah. Okay, good, good. We're okay with that. So now I'm just going to simplify that, right? So this is the same thing as saying x squared plus 1 equals 25. And so that means that if we subtract 1 on both sides, we get x squared has to be equal to 24, right? Now 24 is not a perfect square, unfortunately, right? But that's okay. So this is going to be x is equal to either positive or negative the square root of 24, right? Yeah, remember when you take the square root, right? You get plus or minus, right? Two different solutions, basically, right? But we're talking about lengths of legs in a triangle, right? So if we're just talking about triangles, well, then they always have positive lengths, right? So we can take for granted that this is positive, okay? Fair enough. Yeah, and it's because we're just talking about triangles right now. There will come a point where it does matter whether it's positive or negative in this class, okay? And that point is coming pretty soon. Yeah, not today. So x is equal to the square root of 24. I don't want to leave it like that. That can be simplified, right? And maybe it's been a while since you simplified radicals. So let me start off with an example here. Square root of 72, let's say. Yeah. Well, I'm going to factor 72 completely, right? So 72 is the same thing as, let's see, it's 9 times 8, right? So that's going to be 2 cubed times 3 squared, right? Everybody okay with that? Any questions on that? I did that fast, but I mean, you can reverse engineer that. You see that that's equal to 72, right? Yeah, 9 times 8. Yeah. Okay. Okay, good. So then now, right, I'm going to rewrite this funny way here. This is the same thing as 2 times 2 squared times 3 squared. Yeah, just pulling up perfect squares, basically. That's all I'm doing. And the reason I'm doing that is because square roots distribute over multiplication. Yeah. So this is the same thing as square root of 2 times square root of 2 squared times square root of 3 squared, right? Okay. But the square root of 2 squared is just 2, right? Fair enough. The square root undoes the fact that you're squaring it, right? The square root of 3 squared is just 3. So this is just 2 times 3, which is 6 times the square root of 2. Yeah. Simplifying radicals. Any questions on that? Any questions at all on that? Very handy. It's probably going to make a lot of difference in your MyLab math homework. Yeah. Okay. And depending on how I design the tests, right? If I have multiple choice problems, it's really going to matter also. So, all right. So if we have that, then now let's go back to square root of 24, right? I can rewrite that as, well, let's see, let's factor it completely, right? Maybe you're not as good at factoring as I am, right? So, but you might recognize that 24 is 6 times 4, right? Yeah. So this is 6 times 4. Okay. But now you could factor 6 and you could factor 4, right? So this is the same thing as 2 times 3 times 2 times 2, right? Yeah. And I want to put together as many perfect squares as I can, right? So this is really 2 times 3 times 2 squared. Yeah. Okay. And then now, right, this is the same thing as square root of 2 times square root of 3 times square root of 2 squared is just 2, right? Okay, I can't simplify square root of 2 and square root of 3 though, right? So this is just 2 times the square root of 6. I'll write it as instead. Yeah, yeah. And that's as much as I can simplify that one. Any questions on that at all? Yeah. Now, on the test, right, say we're doing a written response problem, right? I don't expect you to have to show all this work. If you just know that square root of 24 is 2 square root of 6, if you can do that in your head, that's fine. Yeah, so you could skip immediately to this, basically. Yeah. All right. I will be looking for things in simplest form. Yeah, so I may take off a point out of 10 points if it's not simplified enough, right? Something like that. Okay. Okay. So by the Pythagorean theorem, we have that. Now we have the missing side length. That x is 2 square root of 6. Okay. All right. So now that I have that, now we still have to find what sine of theta is and what cosine of theta is and so on and so forth, right? Okay, so I'm going to relabel these as opposite, adjacent, and hypotenuse then, right? So the opposite side is the side across from theta. So then the opposite side is equal to 1. The adjacent side is the side that's touching theta, so that's going to be 2 square root of 6. And then the hypotenuse is the hypotenuse. We all know where that is. That's 5, okay? Yeah, so now I have that. That's everything I need to be able to find sine of theta, cosine of theta, tangent of theta, and so on and so forth. Okay. All right. So I'm going to copy that information back down here so I don't have to keep looking up there. Opposite equals 1. Adjacent equals 2 square root of 6. Hypotenuse equals 5. Okay, there we go. So now, sine of theta. By definition, it is the opposite side length over the hypotenuse length, right? So that's going to be equal to 1 over 5. Okay. Could have done that without even doing that Pythagorean theorem stuff, right? That's sine of theta right there. Okay. You had enough information given to you at the start of the problem. Okay. All right. Now let's go on to cosine of theta. By definition, that's adjacent over hypotenuse, right? So that's 2 square root of 6 over 5. Can't simplify that any, right? Square root of 6 is as simplified as possible already. We showed that when we were factoring it, right? Yeah. And then 2 and 5 don't have any common factors to pull out. So it's just 2 square root of 6 over 5. Can't do anything with it. Okay. Now let's do tangent of theta. Tangent of theta is equal to opposite over adjacent. Open this up just to get some air flowing in here. All right. So opposite over adjacent, right? Opposite is 1. Adjacent is 2 square root of 6, right? I don't like having square roots in the denominator. Yeah. Square roots in the denominator bother me. So I'm going to simplify it. I'm going to rationalize the denominator is what it's called, right? Okay. And so the trick is this, right? Anytime you have like a square root in a denominator like that, let's just multiply by that same square root in the numerator and the denominator, right? So essentially I'm multiplying my fraction by 1 in a funny way, right? Yeah. In order to cancel off that square root. Yeah. Okay. So now that I do that, well, in the numerator, I have 1 times square root of 6. So that's just going to be square root of 6. In my denominator, I have 2 times the square root of 6 times another square root of 6. But of course, square root of 6 times square root of 6, right? That's just square root of 6 squared, which is just 6, right? Yeah. So this is 2 times 6, which is 12. Okay. Square root of 6 over 12. Any questions on that? Did I do that too fast? Are we all okay with that? Eh. All right, so that's a trick we're going to use constantly in this class. Yeah, fair enough. All right, so that's 3 functions there. Let's go on to the next one, cosecant of theta, right? And so the definition of that is hypotenuse over opposite. I'm not going to write that down, though. I want us to get used to the fact that cosecant of theta is just a reciprocal of sine of theta. Okay, it's just the reciprocal of sine of theta. So here I have sine of theta is 1/5. I'm going to take the reciprocal of that, which is 5 over 1, otherwise known as 5. Okay, yeah. Any questions on that? All right, now I'm going to do secant of theta. Okay, now cosine of theta is equal to 2 square root of 6 over 5. So since secant of theta is the reciprocal of that, we're going to get 5 over 2 square root of 6, which we're not going to leave like that, right? We're going to rationalize the denominator. So we're going to multiply by square root of 6 on the top and the bottom again. And when we do that, we're going to get 5 square root of 6 over 12. Okay. All right, one more. Cotangent of theta. That's the reciprocal of tangent of theta, right? So we said that tangent of theta here was equal to square root of 6 over 12. We could take the reciprocal of that, right? Get 12 over the square root of 6, then rationalize the denominator. We could do that. There's nothing wrong with that. However, we also said that tangent of theta was equal to 1 over 2 square root of 6, right? Before we did all of our fancy tricks to it. And that's a lot easier to take the reciprocal of. Yeah. So that's what I'm going to use. So cotangent of theta there is just going to be 2 square root of 6. Save myself some work. Okay. All right. Well, 2 square root of 6 divided by 1, which is equal to 2 square root of 6, right? Yeah. Just kind of show my work so you know where it came from. Okay. Any questions on that? Any questions at all? All right. So there we have it. Sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant of theta, and cotangent of theta. All right. So let's talk about some special angles. Right. Gonna scroll this up a little bit. Let me know if I need to scroll it back down. Can everybody see everything they need to right now? Yeah. All right. So we're going to have a new heading over here. Functions. Function values for special angles. And so you might be asking, like, why are these considered special? Yeah. It's because we can get an exact value for them very easily. That's why. That's the only reason. Yeah, that they're considered special angles. There's like nice, neat little tricks for getting the exact values of these functions for these special angles. That's it. Okay. So we're going to start with 45-degree angles. So if we have a right triangle, we know that one of the angles is a 90-degree angle. If we also know that one of the angles is a 45-degree angle, then that must mean that the other unknown angle is also 45 degrees, right? Yeah, because it has to add up to be 180 degrees. So I'm going to call this a 45, 45, 90 triangle. Okay. Yeah. Everybody okay with that? Okay. Now, let's draw it to the best of our ability, right? No one's perfect. So here we have it. There's a nice right triangle for us. This angle is 45 degrees. This angle is 45 degrees, right? This is our 90-degree angle here, right? Let's just say that this is our theta over here. Okay, fair enough. So remember, we're trying to compute sine and cosine and tangent and so on of 45 degrees. And it doesn't matter how big or small your triangle is, right? As long as it's similar, you're going to get the same values for sine and cosine and tangent, right? So let's just give some scale to this. We can choose whatever scale we want, right? So, sorry, question? No. All right. Well, here's the scale I'm going to use. I'm just going to say this side length is a length 1. Okay. Now, this is an isosceles triangle, right? Because we have 2 equal angles in there, right? So that means that this side length is also 1, right? Fair enough. Okay. And now we can use Pythagorean theorem to find the length of the third side over here. So by Pythagorean, you know what? Let's abbreviate that as PT instead of, just writing Pythagorean all the time. He has a long ass name. So by PT, right? We have that 1 squared plus 1 squared will be equal to the hypotenuse squared. Let's call that C equals C squared, right? So then we get that 2 equals C squared. So then we take the square root on both sides. We get plus or minus the square root of 2. But remember, we're talking about triangles, right? So it's going to be positive. Square root of 2 is equal to c. Okay, so now we have that this third side length is square root of 2. Yeah. So far, so good. Yeah. All right. So then now I'm going to relabel the sides of this triangle, right? The opposite side, the side across from our angle theta, is of length 1. The adjacent side is also of length 1. And the hypotenuse is of length square root of 2. Okay. Any questions on that? All right, so then now let's find values of the trigonometric functions, right? Sine of 45 degrees, which, by the way, that's the same thing as pi over 4 radians. We're going to be using radians a lot in this class, so yeah. Anyway, sine of 45 degrees is opposite over hypotenuse, right? So 1 over the square root of 2, which I'm now going to rationalize by multiplying by square root of 2 on the top and the bottom, right? When I do that, I'm going to get square root of 2 up top, and then I'm going to get 2 downstairs. Okay. So sine of 45 degrees is square root of 2. No, sorry, square root of 2 divided by 2. There we go. All right. Any questions on that at all? Okay. Let's do cosine then. Cosine of 45 degrees is, well, it's adjacent over hypotenuse. Okay, so it's the same thing as sine of 45 degrees, right? And since we've already simplified that, I'm just going to say it's square root of 2 over 2 there. Okay, fair enough. Don't have to show the same algebra steps again, right? Okay, any questions on that? All right, now we'll do tangent. Tangent of 45 degrees is opposite over adjacent, so that's 1 over 1, which is 1, right? It's one of those nice values for a tangent, yeah. Okay. Now let's do cosecant, secant, and cotangent. Feel free to work ahead of me if I'm going a little bit slow. Yeah, I'm sure some of you are very good at this. Cosecant of 45 degrees is the reciprocal of sine, right? So I'm going to use the nice form over here and take the reciprocal of that, right? So we're going to get square root of 2, right? Okay. Now I'll do secant of 45 degrees. I'm going to use the nice form here for that. All right, take the reciprocal and I get square root of 2, right? So sine and cosine of 45 degrees are equal to each other. Therefore, the reciprocals have to be equal to each other also, right? Yeah. Cotangent of 45 degrees, well, it's just the reciprocal of 1, which is 1 over 1, which is still 1. Okay? So cotangent of 45 degrees is also equal to 1. Okay? Okay. So any questions on that? All right. So the next type of triangle we're going to talk about is a 30, 60, 90 degree triangle. 30, 60, 90 triangle. Okay. It's another pretty nice one. Okay, so I'll go ahead and draw a picture of that. Okay. Let's say I draw it like this. And there's my 60-degree angle. Here's my 30-degree angle. There we go. 90-degree angle there. Okay. All right. Now I have to give it some scale. Okay. And so here's the scale that I'm going to give it. I'm going to say that the hypotenuse is of length 2. That's only because I've already done this before, and I know that it just works out better when it's 2. You could do it with 1. You still get the same answer later on for sine and cosine and tangent, right? But I'm going to use 2 for the hypotenuse there. Okay. Now, I don't know anything about this side length, and I don't know anything about this side length, though. Okay. Yeah, I just know that the hypotenuse is of length 2, so I've given it some scale. Yeah. Fair enough. I don't have enough information yet to use the Pythagorean theorem because I only know the hypotenuse. I don't know either of the legs, right? So here's a nice little trick that we're going to do here, right? 30 degrees plus 30 degrees is 60 degrees, right? Yeah. So I'm going to take this triangle and I'm going to mirror it. So I'm going to draw the same triangle over here. Okay. So it's still a right angle over here. Here's an extra 30 degrees there. This is still a 60-degree angle here because all I've done is just mirror it about there. Okay. Fair enough. All right. So then this hypotenuse is still 2, right? Yeah, so that's 2 and that's 2. Okay. Still not enough to use Pythagorean theorem, though, right? Yeah. I just know the hypotenuse in this triangle and the hypotenuse in that triangle. Yeah. Okay. But here's how I'm going to find some of the missing information. Okay. If I consider this angle from here to here, right, this purple angle here, right, well, that purple angle is 60 degrees because it's 30 degrees plus 30 degrees, right? Okay. So if I look at my big triangle, right, which I'm going to do in purple, containing this hypotenuse, this huge side length here, and this hypotenuse, right? If I look at that, that is an equilateral triangle. 60-degree angle, 60-degree angle, 60-degree angle, right? So I'm going to write that the purple triangle is equilateral. Purple triangle is equilateral. And really, I guess technically I should say equiangular, right? But if it's equiangular, then it's also equilateral. The side lengths have to be the same if the angles are the same. Okay. So if that's true, then this whole side length from here to here has to be of length 2 also, right? Fair enough. Now this red triangle and this black triangle are exactly the same triangle, which means that this leg and this leg have to be exactly the same length. So this is of length 1 and this is of length 1. Okay. Yeah. Any questions on that so far? Any questions on that? All right. All right. So now I'm going to redraw my black triangle, knowing what we have now. Okay. So my black triangle looks like this. Okay. This was a 60-degree angle. This was a 30-degree angle. This was of length 2. This was of length 1. Okay. And now I have enough information to use Pythagorean theorem to find the missing side length. Okay. So I'll call that x. Say, call it y or whatever. So I have 1 squared plus x squared is equal to 2 squared, right? Parentheses around that too. Okay, so then we have 1 plus x squared is equal to 4. So then subtract 1 and we get x squared is equal to 3. Right, take the square root, we get plus or minus the square root of 3, but we're talking about triangles, so it's got to be positive lengths. So x is equal to square root of 3 there. Okay, so now we have all 3 side lengths. Okay. Any questions on that? Any questions on that at all so far? Okay. All right. And so now I can choose my theta to either be the 30-degree angle or to be the 60-degree angle, right? Because I have complete information about this triangle now. Okay, let's start off with the 30-degree angle. So let theta be the 30-degree angle. Okay. So then the side opposite the 30-degree angle would be of length 1, right? That's opposite the 30-degree angle. Is everybody okay with that? All right, that change in perspective there. Is everybody okay with that? Okay. So this is the opposite side length right here. Okay. All right, the adjacent side will be of length square root of 3. And the hypotenuse is, of course, of length 2. Okay. Okay, so now I'm ready to do my trigonometric functions, right? I have sine of 30 degrees, right, which is equal to opposite over hypotenuse, right? So that's going to be 1 over 2 is 1/2, right? Okay. Try not to move too fast here. That was not enough coffee. We get out of here at 3:45, right? Yeah, okay, good. Thank you. I've been getting my Monday, Wednesdays confused with my Tuesday, Thursdays. I showed up like 15 minutes late to my class yesterday. I was eating a slice of pizza when a student came in. It's like, "Oh, aren't you coming to class today?" I was like, "Oh, I thought it started at 2:30." Started at 2 o'clock though. Anyway, cosine of 30 degrees. That's adjacent over hypotenuse. So that's square root of 3 over 2, right? Tangent of 30 degrees. That's opposite over adjacent. So that's 1 divided by the square root of 3. And we're not going to leave it like that, right? We're going to rationalize the denominator. So we're going to multiply by square root of 3 on the top and the bottom. And we get square root of 3 divided by 3. Okay. All right. Leg got trapped there. There we go. All right. So now we can do cosecant. Cosecant of 30 degrees is just a reciprocal of sine. So that's 2 over 1, which is 2. And I'll just go ahead and fill these ones out. Secant of 30 degrees, reciprocal of cosine, so that's 2 over the square root of 3. Multiply on the top and the bottom by square root of 3 to rationalize the denominator. And we get 2 square root of 3 over 3. And then cotangent of 30 degrees. I'm going to use the form that's really easy to take the reciprocal of. And I'm just going to get that this is square root of 3 over 1, which is square root of 3. Okay. Oh, by the way, your active engagement assignments, I've already graded them. I haven't put them online yet because I was waiting for my other class to catch up to you guys. And then like I was going to put them all online at the same time. I'll probably have that ready by next Monday then. Okay. Yeah. And so I just wanted to let you guys know. Okay. So now that takes care of 30 degrees then, right? We found all 6 trigonometric functions evaluated at 30 degrees. Okay. Any questions on that? Yeah. Any questions at all? Well, now let's do the same thing for theta equals 60 degrees, right? And that's going to be our active engagement assignment for today. Let theta equal 60 degrees. And then you're going to evaluate the 6 trigonometric functions there. Okay. All right. So again, get out a piece of paper, a whole sheet of paper, not a half sheet of paper. Yeah. They can have fuzzy edges. And evaluate the 6 trigonometric functions. For that 60-degree angle, based on the picture that we drew above. Yeah. Hope you all get 100%. If you have any questions or anything. That would hold the side. So this is the picture I was talking about. Right over here. Right. Okay. Another quick note. I'm recording these lectures, right? And I'm putting the videos online on my university. Now I'll post the views back until the sunlight. Oh, so I use the Pythagorean theorem there. So this side squared plus this side squared equals this side squared. Never been there. Sometimes it's called the master lab. You'll see like signs that say this way the master lab. Looks like their hours of operation this year are Monday through Thursday from 10 to 5. And then on Friday they do some kind of online tutoring also. So yeah, if you're struggling with anything, make sure to just go visit them and ask them. They do tutoring not just for trigonometry, but also college algebra, calculus, math modeling, all the way up to calculus. All right, so are we all ready? Be important in these foundational steps before we move on to the real fun. All right, so let's just go ahead and fly through this one real fast here. Okay. So theta is equal to 60 degrees. I'll recopy my triangle down here just so we can kind of see it. And again, I did not expect you to do this on your papers. So here's my 60-degree angle. Here's my 30-degree angle, right? Here's my opposite side, which is of length square root of 3, right? Here's my adjacent side, which was of length 1. Here's my hypotenuse, which was of length 2, right? Sine of 60 degrees is opposite over hypotenuse, which is square root of 3 over 2, right? Cosine of 60 degrees, I think I write better on a flat surface here. Cosine of 60 degrees, adjacent over hypotenuse, tangent of 60 degrees, opposite over adjacent. Okay. Now we have cosecant of 60 degrees is reciprocal of sine, so that's 2 over the square root of 3, right? We're going to rationalize it. We're going to get 2 square root of 3 over square root of 3 times square root of 3 is just 3. Secant of 60 degrees will be equal to the reciprocal of cosine, which is just going to be 2 over 1, which is 2. And then cotangent of 60 degrees is going to be the reciprocal of tangent, which is going to be 1 over the square root of 3. We're going to rationalize it. So we're going to get square root of 3 over 3. Okay, and there we have it. So there's your active engagement assignment there. Okay. Any questions on that, by the way? All right. So now that we have that, I don't know if this is really the right section for this, but they start introducing identities. So I figured, all right, let's go ahead and do it. So this is very different than the way that I used to cover the class anyway. So fundamental identities. Okay, so in case you forgot from college algebra, an identity is an equation that's always true for everything in the domain, basically. So everything that you can plug in. So here's an example of an algebraic identity here. It's going to be kind of silly, probably. 2x plus 4 is equal to 2 times x plus 2. Yeah, that's an identity. It's true for every single x value, right? Fair enough. Okay, so as long as it's true for every single x value, that's an identity. So let's talk about some trigonometric identities then. Okay, and we're going to start with easy ones. The reciprocal identities. Reciprocal identities. All right. So the reciprocal identities are like this: sine of theta equals 1 over cosecant of theta. Right? They're reciprocals of each other. Yeah. And so that also must mean that cosecant of theta is equal to 1 over sine of theta, because they're reciprocals of each other, right? I can do the same thing with cosine and secant. Cosine of theta is 1 over secant of theta. And then secant of theta is 1 over cosine of theta. Right. And then I can do the same thing with tangent and cotangent. Tangent of theta equals 1 over cotangent of theta. And cotangent of theta is equal to 1 over tangent of theta. Okay. I don't think I really need to explain that any more than I already have, right? So we've been using the fact that they're reciprocal to each other all along, right? According to the definition, sine is opposite over hypotenuse, and cosecant is hypotenuse over opposite. So they're clearly reciprocals of each other, right? And so that's true for all theta, right? For all theta that you can plug in, right? What do I mean by that? I mean that there are some things, some theta values that cosecant is not continuous for, and we'll talk about that when we start talking about the graphs, the functions. Okay. Yeah. Okay. Okay. So any questions on that? All right, so the reciprocal identities, great. Let's talk about it a little bit more. How about the quotient identities? Quotient identities. This one might require some explanation. So I'll give you the quotient identities first, and then we'll kind of justify it. Tangent of theta is equal to sine of theta over cosine of theta. And cotangent of theta is equal to cosine of theta over sine of theta. Okay, let's go. Yes, yeah, sorry. Handwriting's awful. There we go. Tangent of theta. Yeah. All right, so let's justify that, right? So tangent of theta is equal to opposite over adjacent, right? According to the definition, right? Now sine of theta over cosine of theta. Let's see if we can simplify that. Okay, so sine of theta is all in the numerator here, right? Is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse, right? So I have a fraction divided by a fraction, okay? Now, some of you may know this as keep, change, flip, right? Yeah, whenever you have a fraction divided by a fraction, you have to keep, change, flip, right? The way that I always learned it in high school was whenever you have a fraction divided by a fraction, it's the first fraction times the reciprocal of the denominator fraction, right? That's the way that I always learned it. And it's just easier for me. Yeah. So here I'm multiplying by hypotenuse, but I'm also dividing by hypotenuse, so they're going to cancel off. So all I have left over here in my numerator is opposite. All I have left over in my denominator is adjacent, right? So sine of theta over cosine of theta is also equal to opposite over adjacent. Therefore, tangent of theta is equal to sine of theta over cosine of theta, right? Fair enough. Call that a little note there. Questions on that? Any questions? All right. You could do the same thing with cotangent of theta and show that that's equal to adjacent over opposite if you simplify cosine of theta over sine of theta. Okay. Yeah, exactly the same step, so I'll skip past that. Okay, so what can we do with these identities? Well, let's find out. Okay, let's suppose theta is an angle in a right triangle. And that sine of theta is equal to 1 divided by the square root of 5, right? And if 1 divided by the square root of 5, and I don't like leaving it like that, so I'm just going to go ahead and rationalize it now. Square root of 5 over square root of 5. So we get square root of 5 over 5. Just an alternate way of writing sine of theta. Yeah, okay. Find the values of the 6 trigonometric, or, well, 5 other trigonometric functions of theta, of the trigonometric functions of theta. Trigonometric. It's a tricky word. Of functions of theta. Okay, so that's our goal here, right? I want to know what cosine of theta is. I want to know what tangent of theta is, and so on and so forth, right? Knowing only that sine of theta is equal to 1 over the square root of 5, I want to get that. Okay, yeah. So let's see what I can do here. Let's start off this way, right? I want to use some trigonometric identities, right? So I'm going to say that, well, how about the reciprocal identity? We know that sine and cosecant are reciprocals of each other, right? So cosecant of theta is equal to 1 over sine of theta, right? And you could literally take what sine of theta is there, right? Square root of 5 over 5, and you could put it in the denominator, right? And you could simplify that if you wanted to, but that's kind of the hard way. That's kind of the hard way of doing this. Here's the easy way. Sine of theta was first given to you as 1 divided by square root of 5, and that has a very nice reciprocal, right? So then cosecant of theta, which is the reciprocal of sine of theta, will just be square root of 5 divided by 1. So then we have automatically that cosecant of theta is equal to square root of 5 using our reciprocal identity. Okay. We were doing that before anyway, right? Before we would call it a reciprocal identity. Yeah. All right. So now that we have that, right? Well, how do we find cosine of theta, secant of theta, tangent of theta, and so on and so forth? Well, the only option we have now is to draw a right triangle. Okay. So all we know is that sine of theta is equal to square root of 5 over 5. Okay. Okay, and now we have to draw a triangle that represents that. We need a triangle with an angle theta in it such that sine of theta will be equal to square root of 5 over 5 within that triangle. Okay, yeah. So here's how I'm going to do it. Sine of theta is always defined to be opposite over hypotenuse in a right triangle. Okay? So let the opposite side be of length square root of 5, and the hypotenuse be equal to 5. Okay? So I'm going to draw me a right triangle now. And I don't care if it's accurate or not, if it's to scale, right? I'm going to put an angle theta in it. And I'm going to say that the opposite side is of length square root of 5, and the hypotenuse is of length 5. And there we have it. There's a triangle where if I were to take sine of theta in there, I get square root of 5 divided by 5. Okay? So this triangle is representative of the equation sine of theta equals square root of 5 over 5. Okay. So I'm going to pause here for questions. Yeah. This concept is something we're going to use a lot in this class. So, yeah. Any questions on that? Any questions at all? No. Okay, good. So now that I have that, right, I have a missing side. Use Pythagorean theorem. By Pythagorean. Oh, right. We're rewriting that now. Okay. There we go. By PT. By Pythagorean theorem, we have that, call this side length x, right? X squared plus the square root of 5 squared is equal to 5 squared, right? Okay, so this is x squared plus, well, the square root of 5 squared is just 5, right? 5 squared is 25. So then x squared is equal to 20, right? Now, that means x is equal to plus or minus the square root of 20, right? But of course, we're talking about lengths of sides in a triangle, so it's positive square root of 20, right? Now we're going to simplify that. That's 4 times 5, right? All right, so that's the square root of 2 squared times 5. So then we're going to get the square root of 2 squared is just 2 times the square root of 5. Okay, so that's my missing side length there, 2 square root of 5. So I have that my opposite side is of length square root of 5. My adjacent side is now of length 2 square root of 5. And my hypotenuse is of length 5. And that's really all I need in order to find sine, cosine, tangent, cosecant, secant, and cotangent of theta, right? So let's just write out all 6 of them. Why not? Okay. Sine of theta was given to us anyway, but I'm just going to rewrite it as square root of 5 over 5, right? Cosine of theta, adjacent over hypotenuse, so that's 2 square root of 5 over 5. Okay. Tangent of theta is opposite over adjacent, right? So we're going to get square root of 5 over 2 square root of 5. Okay. So here I have a square root of 5 in a numerator and denominator, right? They're common factors, so I can cancel them off, right? So they cancel to 1. So my numerator is now 1. My denominator still has a 2 in it, right? So it's 1/2. Okay. So there's my tangent of theta. Any questions on that? All right. We already found cosecant of theta above, right? Yeah, so we've used the reciprocal identity. It's just square root of 5, though, right? Okay. Now let's find the reciprocal of cosine. Right? So secant of theta will be the reciprocal of cosine, so that's 5 over 2 square root of 5. Got to rationalize it. All right, so we get 5 square root of 5 divided by, well, 2 times 5 is 10. We can totally simplify that, right? 5 divided by 10 simplifies to 1/2. So this is square root of 5 over 2. Okay. Cotangent of theta is just a reciprocal of tangent, so 2 over 1, which is equal to 2. Okay. Any questions on that? Ooh, this is a good one.